Yes. So now let us put all of these things here. So this is I2. Let me, before I put the results there, let me have this. So what I have here is, this is one term which is T times del 2 sigma del sigma square F mu delta x mu, and this another term minus T d tau into x prime mu delta x mu, and this is over the surface boundaries of sigma. Okay, good. And so, and I1 was there. Now here you start getting the feel for the first time about the string theory. Now here the time boundary term for I1 was always 0 from tau equal to minus infinity to tau equal to plus infinity. Here the boundary terms would again go to 0, but how? That would depend on the different cases of the closed string theory, open string theories, and what kind of open string theory, what kind of boundary conditions you take, Neumann boundary conditions, or Dirichlet boundary conditions, or Neumann-Dirichlet boundary conditions, or Dirichlet-Neumann. Because open string will have two ends, a closed string would have no free end, but open string will have two free ends. And I can have Neumann boundary condition here, Neumann boundary condition, and I can call it, or Dirichlet boundary conditions, or Dirichlet-Neumann, or Dirichlet-Neumann. So I can have different boundary conditions at the two ends of the open string. But somewhere in our mind we know that the boundary terms have to go to 0. So the boundary conditions have to be defined in such a manner so that the boundary terms always vanish. That's the main thing. And how we do it, that defines what kind of a theory you are handling. Closed string theory, open string theory, which kind of open string theory, which kind of boundary conditions. So this feel you actually start getting only after we have obtained the equations of motion. We are still in the process of obtaining the equations of motion. We have not yet really obtained, because these terms are still hanging around. We have to do something with them, and we have to try to understand them. We have to make some sense out of it. Okay, so very good. Now this you can write. So actually let us differentiate in this term, which is always going to be there, and this, if you like, I could call it as a boundary terms, okay, or boundary terms. So this we can separately talk about the boundary terms. Let me record this on this side. Let me record it on this side. So I2 is T d2 sigma into plus del sigma square x mu delta x mu this, okay, plus boundary terms, and so this del sigma boundary terms, okay. So we write the sigma boundary terms. These are the terms minus t d tau x prime mu delta x mu and your sigma equal to, okay, let me still call it like that. Okay. So now, but now I can remove all the way up to here. If you like, one thing I could already say, delta S, which was my equal to I1 plus I2, let me yes, this was delta of this. So let me combine those two terms there, which would be T d2 sigma into minus del tau square plus del sigma square x mu into delta x mu. This is always going to survive, plus the boundary terms. So let me not take more space here, because and boundary terms over sigma. The sigma boundary terms are still there. So you can already see it that when somehow we drop these boundary terms here, then only this would survive, and because this would be non-zero, so this equal to 0 would give me my equations of motion for the Polyakov action. However, let us now get back to the boundary terms. So the sigma boundary terms. So now we go case-wise. Case. So we can okay, so here I was a bit lost in my papers. So we want to talk about this boundary term, which is minus t d tau x prime mu delta x mu over this sigma. Now let us first consider the closed strings. Okay, we first consider the closed strings. Now here for the closed strings we apply periodic boundary conditions. So we would like sigma to have periodic boundary conditions for the closed string. So which means we would like to have x mu of tau sigma equal to 0 equal to x mu tau sigma plus L, or this could also be called as tau sigma plus 2 pi for the closed string. This is L plus 2 pi. So we say that this is equal to this, and now so there are a few simple alternative descriptions to understand how these boundary terms vanish for the closed string. One simple way, the simplest argument, you say a closed string has no boundary, and therefore the boundary term should not be there. That's the most simple kind of a thing which comes to the common sense. Okay, it should have no boundary and there should be no boundary term. That's the one thing. But we can put it slightly in a mathematical form. So this is minus t d tau, and this is the one which is already being evaluated. So x prime mu delta x mu at sigma equal to at